Just a quick mic check. Can everyone hear me? Okay. Okay, so let's get started. Just to check, I believe this is where we left off. We were just about to start talking about Le-Chatelier's principle. Anybody remember? Okay. So by definition, if I wanted to just simplify Le-Chatelier's principle into one definition, it is just simply the homeostasis for chemistry. So it's always trying to adjust itself back to the original value at equilibrium. So if something is at equilibrium, we're going to assume it's dynamic equilibrium, so it keeps changing on its own. If something disturbs this, it will try to undo that disturbance to return to being at equilibrium. Any questions so far? Okay. So once again, it's going to either shift to the left or right. So in other words, we're going to make more product or make more reactant as a response to whatever happens in terms of its change. Okay. Does anyone need time with this before I move forward? Okay. So we're going to look at three different effects. Sorry. First one is going to be a change in concentration. Next one's going to be change in pressure, also known as change in volume. And the last one's going to be change in temperature. So change of, well, if I look at an example here, I have A changing into B. So I'm just going to go ahead and draw that for you here. We'll assume this is at equilibrium, okay? So if I increase the concentration of A, if this is already at equilibrium, the system's going to respond by using up that A. So it's going to shift to the right to use up that A. And the same could be said if I decrease the concentration of B, it's going to shift to the right to make more of my B. Okay? And then the opposite is true. If I decrease A or increase B, it's going to shift to the left as a response. So something initially happens when it's at equilibrium, and then you shift as a response. We are looking at that shift. Any questions?
Professor, basically, it's just if you add more of A or B, it'll try to balance it out again. Is that basically all
It'll
it
try to
is?
use it up.
Okay.
On the position of K itself, the value of K does not change. So let's say this value of K here, I'm just going to make up a number, happens to be 3/2 or 1.5, right? So at all times, if this is at equilibrium, then I should have 3B and 2A's, okay? If I somehow add more of one or the other, it's going to go ahead and shift things around to balance it so that it becomes 3/2 again. Does that make sense? Take your silence as a yes then.
Yeah, sorry. I realized I was muted.
Okay. So just to give you another example of this, if I take a look at an example here, I have PCl3 plus Cl2. That changes into PCl5 and reverse as well. So at any point, if I increase either of my reactants or I decrease my product, it will shift to the right as a response. Oops, sorry, there we go. Once again, if I increase either of my reactants or decrease my product, it will shift to the right as a response. If I increase my product or decrease my reactant, it will shift to the left as a response. Okay, any questions? All right, let's continue. So we have a lot of before and afters. If you notice, this is almost like writing an ice table right here. So same concept here. This is at equilibrium, okay? What happens here is I went ahead and I added it some chlorine in. When I add some chlorine in, it's going to try to undo that add. So what's going to do is it's going to go ahead and take some of this and change it to PCl5. So we're going to use up more of our reactants to make more of our products. So it's minus X of some amount. It's plus X of some amount. By the time we're done figuring out, it comes out to about 0.037 of a difference. Okay. It's going to shift in that direction to, again, use up that Cl2 that was added in. Does it use up all of it? There's no guarantee that it will, but it uses up some of it to try to undo that change. Any questions? All right. So another example of it here. For those of you taking the lab, you may come across the equilibrium lab. I don't know if they changed it since then, but anytime we add in something, so add in a reactant or product, by the time we're done balancing everything out to make sure that the K is still the same value, your overall amount has increased. So you should have more of your reactant and your product. If you take away some, by the time you're done, you should have less of it. So an example you can see right here, if I go ahead and take away some, right? Or even if I, in this case, sorry, I'm adding some here. So by the time I'm done, this should increase. The amount that this is here should decrease, but the overall amount should be a slight increase because you've added more into this whole thing. Until it's done balancing itself out, there's still going to be more of it present. Any questions? Okay. So the next thing we're going to look at is the change in pressure. The best way to look at this is actually through volume. So we don't really want to look so much at pressure. We want to look more at the volume itself. Okay. Really quickly, we're going to focus only on gases. What can you tell me about gases? What are some properties of gases? What do they tend to do? Move around quickly. Okay. So they move a lot. They collide. That is true. If I have gases in this box, do they just sit in one area or do they spread across everywhere? They fill the entire container, right? If you started with a small amount of gas, it's going to spread in every location. It's going to just completely disperse and spread apart. Okay. Then if you make the container even larger, it's going to spread even further. That's just the nature of gases. Okay. And we can use that to our advantage here. So we're going to go ahead and look at this in terms of increasing pressure means decreasing volume. So if my pressure goes up, I'm going to assume my volume goes down. Okay. We're going to go with that assumption for now. If I have less space, the atoms are going to go ahead and condense itself into that less space. It's going to adjust so that it takes up less space. If I have more space, it's going to go ahead and adjust so it takes up more space. Does that make sense? Take your silence as a yes. Okay. So a couple of things we can do. If we change the concentration that is present, it's going to shift in the direction according to the same change in concentration. If I add an inert gas, so a gas that does not react with my reaction, then it will have no effect as long as our overall volume does not change. Okay. So let's look at this in terms of the number of moles of gas. So I have a favorite example that I always like to use. I like to always use the synthesis of ammonia. So if you look here, I'm assuming these are all gases. You have to make sure this is balanced. So you have to go ahead and put a 3 here, a 1, and a 2 there. Okay. In terms of the moles of gases, how many moles of gases are here? In total? 4. Okay. How many on the right side? 2. Okay. So normally, if we shift from left to right, it should condense itself, making more of our NH3 so that it takes up less space because the number of moles here is less. Okay. So what's going to happen here is if I decided to change the container that this is in, so I'm assuming this is at equilibrium. If I change the container and I set it from a small container into a large container, the reaction is actually going to shift to the left in this scenario to make more moles in order to fill up that space. Okay. If I go the opposite direction, I change the container into a smaller container, it's going to shift to the right to take up less space. And so it ultimately depends on which way our moles of gas are, which one has more moles, which one has less moles. So it's never a guaranteed shift to the left or right when we're talking about changing in sizes and changing in volume, because it depends on the number of moles on each side. Any questions so far? Okay. And once again, if we change the volume, also known as our pressure, then it has no effect on the actual value of K. Our K stays the exact same. So looking at the scenario here I have 2 moles of gas. Here I have 1 moles of gas. Okay. If I lower the volume, lower the pressure and raise the volume, so I have more room here. This is going to go ahead and shift to the left. It's going to make more of my orange and blue and use up some of my green. So I should have less green here, more of my orange and blue, just to fill up the space and take up that room. If I go in the opposite direction, I lower the volume by increasing the pressure. There is less space here. So if there is less space, it's going to go ahead and shift to the right. The orange and blue are going to combine and make more green to take up less space. Any questions so far?
Wait, Professor, why would that be?
Why would that be? Let me give you an example. We'll use people as an example, okay? Let's say you are in our classroom. We'll just say a classroom that's the size of like 30 by 30. Okay, everyone's standing there. Suddenly the ceiling drops down to about half the height of the room. How would you as a person respond?
I bend down.
How would you respond?
I'm not sure if the ceiling went
If the ceiling
halfway
starts
down.
coming down and it comes down to about halfway down the room, how would you as a person respond? Would you just stand there and look at it?
Try to get smaller.
You try to get lower. You would respond by ducking down, right?
Yeah.
So it would be the same case. So if you look at the scenario here, the container has gone down. So these gases want to go ahead and take up as less space as possible, a little space as possible. So the best way to do so is to change it into more greens.
Okay. I
Okay.
understand. Yeah.
Okay, let's continue. Now, the last one we're going to talk about is the change in temperature. So this one depends on whether the reaction is endothermic or exothermic. Okay. So I'm going to give you an example here. I'm just going to make this up right here. A plus B changes into C, and we'll say plus heat. Is this exothermic or endothermic?
Exothermic?
It is exothermic, right? Heat is leaving on the right side. So the way this works is if I go ahead and increase the temperature, what happens is both the forward reaction and the reverse reaction speed up, okay? But the only difference is the location where the heat is, it speeds up more. So this is gonna go even faster, okay? And so as a response, how the reaction is gonna respond is it's gonna shift to the left to undo that extra heat. So you can treat heat almost as if it was an actual item, like it's a product or a reactant, okay? If I increase the temperature, both sides heat up, both sides increase in their reaction, but the heat increases even more. So if this increases even more, as a response, it's gonna shift to the left to undo that heat. Any questions so far?
Wait, could you just re-explain that real quick, please?
Sure. Let me go ahead and open a whiteboard. Maybe that might be a little bit easier to share with you. Okay. So really quickly, we're going to look at two scenarios. This is just my exothermic reaction, okay? Heat is located on the right side. If I increase the temperature, any reaction I increase the temperature of, both the forward reaction and the reverse reaction speed up. So I'm going to put an arrow here and an arrow here, okay? The only difference is if this is an exothermic reaction, this one speeds up even more. Okay, so we're going to have essentially double the speed up here. So I have an increase in the heat. How is this reaction going to respond? It's going to respond by it's going to change it to the left to use up that heat. We have extra heat here. Okay, so as a response, it's going to shift to the left. Does that make sense?
So this is when heat is added, right?
This is when heat is added for an exothermic reaction.
Okay, thank you.
Okay, if, however, I decided to lower the temperature, what's happening here is this side is lowered. Remember, this is a double-edged sword. You can think of it that way. So when I go ahead and lower the temperature, I lower it more effectively on this side. So heat is being lost on this side. As a response, the reaction is going to shift to the right to make up for that heat. Actually, to clarify, no, it doesn't mean more space or less space. It depends on how many atoms you have on each side.
What the fuck are you saying, babe?
I'm trying to get your attention.
I'm going to go ahead and mute you real quick. All right, so let's continue. Now, once again, this is what we're talking about in terms of exothermic reactions, okay? Now let's talk about this in terms of endothermic reactions. Endothermic reactions is like this. Heat is now located on the left side. Okay? Is everyone following along so far? Okay, with that said, I'm going to go ahead and increase this temperature. When I increase the temperature, this is going to heat up twice as much. This is still going to increase. But as a response, this is going to shift to the right to undo that extra heat. So you notice in this first scenario here, because it's exothermic, it shifted to the left. And this one here, because it's endothermic, shifts to the right. So in both scenarios, just because we said it increased heat doesn't mean it shifts right or left. Depends if we have exo or endothermic. Okay? Now, same thing here. If I go ahead and I lower the temperature, this lowers twice as much. This lowers just a little bit, okay? So as a response, this reaction is going to shift to the left to make up for that. Is anyone still confused about this?
Wait, so the one you just explained was the endothermic version?
Yes, endothermic is the heat is on the left side of the equation. Exothermic heat is on the right side. So it depends on what kind you have, exothermic or endothermic, and it depends on what you're doing to it, increasing temperature or decreasing temperature. Does that make sense?
Wait, so in the first one, in the exothermic, because the heat is increasing, the reaction is gonna proceed to the left.
So I want you to imagine this, okay? If you're getting confused about this, look at heat as if it was a piece of this, as one of these,
Yeah.
okay? So you can call it D if you have to. When I increase the temperature, I'm increasing the heat. So as a response, it shifts to the left,
Okay.
okay? And the opposite, if I decrease the temperature, it's decreasing this, so it's going to shift to the right as a response. So if you treated it as if it was a concentration, it would be almost the same exact concept, okay?
Yeah.
But I want you to remember that when you increase the temperature, both sides increase, so this one increases more. And again, Ashley, to clarify, it depends if you have exothermic or endothermic reactions. So going back to volume, just to clarify here, is everyone okay if I clear the screen right here? Anyone need time to copy it down? It's not in the notes or anything. Okay. So going back to dealing with pressure and volume, okay? If I said here, I have 3 moles of gas and 2 moles of gas. In this scenario right here, if I increase my volume, right, also known as decrease of my pressure, it's going to shift to the left as a response. There's more room. It's going to go to the side where it can make more, okay? If I flip the scenario, I decrease the volume, aka increase the pressure, it's going to shift to the right as a response. That's only for this scenario right here because this is 3 and 2. If I flip the scenario on you and I said I'm looking at a 1 and 2 scenario, then everything just flips around because this side has more. So again, if I go ahead and I lower the pressure, increase the volume, it's going to shift to the right as a response to use up that extra space. So it's dependent on which side has more atoms of or moles of gas. Does that make sense? I'll take everyone's silence as a yes then. Okay, let's continue. So there is one special thing about temperature. When we go ahead and look at temperature, remember, temperature has an exponential effect on the rate, right? So that means it also has an effect on our big letter K. So our K actually changes with temperature. So the equation down here should look kind of familiar to you. We've seen maybe 2 other of these same exact equations. This is known as the Van Hoff equation now. So once again, this is related to the big letter K, not the small letter K. Any questions so far? Okay. With that said, let's talk about catalysts. So catalysts, really quickly, they speed up the forward and the reverse reaction. So both sides speed up. So we get to our equilibrium faster, but we don't change the position of the equilibrium. So the equilibrium stays exactly where it should be. It just helps us get to equilibrium faster. Any questions? All right. So to summarize everything, you can find this on table 17.4 in your textbook. You have everything with concentration here, pressure, also known as your volume, temperatures relationship, and a catalyst relationship. Okay. So,
Professor, can I ask a
yes.
question? I'm not sure if it's a question about the catalyst from the quiz. I'm not sure if the other class or the other session.
You can ask me after next week.
After next week? Okay.
Yes.
Okay.
Okay. All right. So back to this right here. Let's go ahead and see if we can answer the shift left or right as quick as possible. Okay. Let's take a look. Oh, this is going to focus on specifically one topic. So it's going to focus on water here. So if you go ahead and shift in one direction, let me go ahead and just draw this out so you can see it. When we shift in one direction, what that means is if I shift to the right, I increase in the amount of these two and I decrease in the concentration of these two. Does that make sense? Just wanted to make sure that that's clarified. When we shift in one direction, we're still changing between both sides, but it's going to change more of my AB into CD. It's going to be faster that way than CD into AB. That's what we mean by shift. Okay, so with that said, let's look at the first one here. I am adding some O2. Which direction will this reaction shift? Left or right?
It would shift to the right.
It will shift to the right as a response, okay? So if the shift to the right, that means I have more of H2O, so this is going to increase, okay? With that said, let's look at the next one. I am adding more O2 still. It's going to shift to the right. What happens to my H2S?
It's gonna decrease.
Decrease, right? Because we use up more O2 and more H2S to undo the extra O2 that we added. So it's going to make more of the stuff on the right. Okay, with that said, if I take away some H2S, remember when we take away, we're not taking all of it away, we're taking some of it away. How is this reaction going to shift or respond?
It's gonna be the same thing. It's gonna have more O2. It's gonna be more to the right. It'd be shifting to the right.
So you're removing
it'd be-
H2S.
Oh no, it wouldn't change. Cause
It would
there's
change.
not enough it wouldn't be enough reactants though, no?
So I want you to imagine this as a before and after, okay? So the before is I take away this value, H2S, okay? I'm not taking all of it away. I'm taking some of it. Does that make sense?
Oh, so then yeah. And then it's gonna shift to the left.
As a
to
response, it's
respond.
going to shift to the left, okay? And because it shifts to the left, I made more of this H2S. I also made more of O2, okay?
All right, thank you so much,
So
Professor.
this should be increasing. Okay, any questions on this? All right, so let's get past all this. This is just the detailed of it. We don't need that. Let's take a look at this, okay? We are looking at the relationship between volume, in this case. In the first scenario, how many moles of gas do I have on the left and right? We're gonna write numbers on this, okay? How many moles of gas on the left? I would double check that. Remember, when we're dealing with volume, it's only for gases. This is a solid. Okay, how many on the right? 1, okay? The next one here, we know we have 3. This one has 1. This one has 2, and this one has 2, okay? So with that said, I want to increase the yield of the product. So I want it to shift to the right. That is my goal, okay? If I want it to shift to the right, for the first scenario, do I want to increase the volume or decrease the volume?
Increase.
Increase my volume, also known as decreasing my pressure, okay? So in this one, I want to increase my volume. So when it has more room, it's going to shift to the side. That can make 1 mole of gas. The 0 is not going to affect it at all, so we're going to shift to the right. In the second scenario, do I want to decrease or increase the volume?
Decrease.
You want to make sure it's a smaller container. When you squeeze it together, you're forcing these two to join together. You're making more of this, okay? And in the last scenario, which one do I want to do? Increase or decrease the volume? Okay, someone said decrease. No matter what you do to it, pressure-wise, it will not make a difference. Because both sides have 2. So increasing or decreasing the volume does not make this reaction shift in one direction or the other for the last one. Okay, so let's go through this quickly. Has no effect for the last one. Okay, let's take a look at temperature. So to help you out with temperature, again, if you're getting confused, find out if this is exothermic or endothermic and draw the heat on the correct side and then figure it out. Okay, so the first one we have exothermic. Where's the heat?
On the right side.
Okay, I'm just going to write plus H because I'm lazy. And then this one is on the left side. This one is on the left side. Okay, so we're going to look at an increase in temperature. So I'm increasing my overall temperature. Okay, which way is this reaction going to shift if I increase the temperature for the first one? going to shift left, okay? And the second scenario, wherever your H is, it's going to shift to the other side of where your H is not, because we are increasing the temperature. If I decrease the temperature, it's the opposite effect. It shifts to the side where the heat is located. Any questions? Okay. So just as I mentioned, all the stuff here. Now, let's go ahead and take a look at the synthesis of ammonia. So this is the equation in front of you. You know that this is an exothermic reaction. You know that there's 4 moles of gas and 2 moles of gas. So on the left and the right, respectively. Go ahead and find 3 ways to maximize the yield of NH3. So the best way I can go ahead and get more NH3 out of this. Let's say you work for a chemical company and it says, you're given this reaction, you're giving this amount of reactant, this amount of product. I want you to maximize the amount of NH3 that you can get out of this, and I will pay you for that experiment or for that skill without adding more stuff into it. So you're not given more than what you have right now. What can you do to increase the yield of NH3? Okay, I guess no one wants to work for a chemical company.
Professor, I just found out 2.
Say it again.
I only found out 2.
You only found 2? Okay, just name them.
Decrease temperature.
Okay, so let's write down where the heat is. Heat is located on the right side, right?
Yeah.
If I decrease the temperature, it's going to shift to the right as a response to make up for that heat. So that is one method, okay? If we go ahead and decrease our temperature. Ashley, you said increasing the volume. Increasing the volume would actually not benefit us because there are 4 moles of gas here, 2 moles of gas here, okay? So you actually want to decrease the volume. You squeeze this container, you're forcing more of the N2 and H2 to join together to make NH3. So a decrease in the volume would also shift to the right. What's our third method? So to answer your question, yes, we can add more reactants. But then the chemical company is going to say to you, well, if you just add more reactant, yeah, you can make more product, but I'm not paying you to do that. Removing the
can't.
product. That is the
Yeah.
correct answer. We go ahead and take NH3 out as it is being made. We make some NH3, I take it out. The reaction is going to say there's not enough NH3. I'm going to keep making more. It's going to keep shifting to the right as a response as long as you were taking out the NH3. Okay. Now, obviously, we can do many other methods. We can add more N2, we can add more H2, all those, but it costs more money to do that. So the most cost efficient way is to go ahead and remove some NH3. Okay. Removing NH3 as it forms, decrease the volume, also known as increase the pressure, and decrease the temperature. Any questions? Okay. So this is just a relationship between the temperature and the value of K. As we increase in the temperature, we actually decrease in the value of our K value. Okay. This is just to show you the relationship. Again, this is for an exothermic reaction. All right, let's continue. So some ending reminders to write down. When you're dealing with your equilibrium expressions, remember that your coefficients are your exponents. And we don't include solids and liquids in our equilibrium expression, only gases and aqueous solutions. Your ice table is going to be your new best friend. Get used to using it. You will use it for the rest of this semester. Okay, so this chapter, next chapter, and each chapter after that, you will be working with some form of an ice table, at least once or twice. Always go ahead and try to assume the 5% rule first. If you can't, you can go ahead and use the quadratic equation. So always try to find a way to not use the quadratic equation. If you have to in the end, then you have to, okay? I will tell you one thing. For the purpose of the final exams and the ACS exams, usually you get about 2 minutes a question. So they will never, since I've been teaching here, they will never ask you a quadratic equation because there's always some way to remove that change minus x plus x, okay? because a quadratic is going to take too long for you. So out of our Le Chatelier's principle, only temperature will change our K and our equilibrium expression. The other ones will not affect it. They will cause a shift, but they will not change the actual value of K. Any questions so far? Does anyone need time to copy this? Okay. So something to help you remember Le Chatelier's principle. Okay, so we're going to go ahead and transition over to chapter 18 now. Okay, I'll give you a minute to settle in if you need, and then we're going to get started with chapter 18. Any questions before we begin? Okay. So chapter 18 is about acid-base equilibria. So we're going to learn about acids and bases, the different models of them, how to calculate the concentrations of each one. If you notice the word equilibria, that means we're still dealing with equilibrium in here. Okay. So we got 3 models of acids and bases. The first one is called Arrhenius acid and base. And I'll just briefly talk about each one for now. We will visit each one in more detail. The first one, Arrhenius's acid and base, is based off of water. It says that water is going to separate into H plus and OH minus. The H plus is anything that produces H plus is considered an acid. Anything that produces OH minus is considered a base. Bronsted-Lowry says that that's not necessarily wrong. He's referring to Arrhenius's definition, but he expands it on it. He says that we can't limit it to just things that make OH minus for the definition of a base. So it has to have lone pairs of electrons that it could deal with, right? It also has to be something that can actually receive protons. So acids are proton donors, bases are proton acceptors. Lewis expanded on the definition further, says that's not the best definition. We can expand further. So he says that we're going to look at things instead of on protons, we're going to look at things in terms of electrons. So he looks at for electron pairs. So for the first one, it's an electron. The acid is an electron pair acceptor. So instead of being the proton donor, it is an electron pair acceptor. And then the base is an electron pair donor. Once again, we're going to revisit each one of these. I'm just giving you the intro to it. Okay, so Arrhenius's definition, just as I mentioned, is based around water. This will yield H3O plus. In other words, I like to refer to it as H plus sometimes. So if you see H plus or H3O plus, it means pretty much the same thing. This is your hydronium ion. This is just your hydrogen ion. Okay. And then bases will yield OH minus. So in a solution down here, the acid plus the base should make water. Any questions so far? Okay, let's continue then. So we have a couple of terms for strong and weak acids. So a strong acid, remember, a strong acid doesn't mean that it's, a strong acid and a weak acid. This doesn't mean that one is dangerous and one is not. Both can be very dangerous to you, okay? Strong acid means it dissociates completely. That means it easily breaks down into its individual ions and makes a lot of H plus. A weak acid still breaks down H into H plus, but there's less H plus present. Okay, so some examples I can give you. Once again, a weak acid does not mean that it is not dangerous. So the level of dangerousness is nothing to do with the terms strong and weak. This is just simply how much it's associated into the solution. Okay. Any questions so far? Okay. So we have an equation here. That's with K, right? We have your H plus solution here and then A minus. This is A minus usually refers to whatever's left over. So if I'm looking at something like HCl, this is hydrochloric acid. If I take away the H, the Cl minus is my A minus. It's just whatever is left over. So with that said, if I'm looking at a weak acid, the ratio here, remember HA is not going to go ahead and do anything. H2O is definitely not going to do anything here. The concentration between H3O plus and A minus, this is a very small number, okay? It's going to be so small that we just call this K value very, very tiny. So that's what we're referring to. There's going to be very little of this H plus present. And there's very little H plus, there's also very little A minus. So to give you a visual understanding of what's going on here, if I have a strong acid, HA, whatever HA represents, okay? It will, when I put it in water, it will completely dissociate. So all of the H plus will break away from all of the A minus. So your solution just simply becomes H3O plus, this is your acidic portion, and then you have A minus, whatever is left over. So you have no HA left over from the beginning, okay? In this scenario, if I'm looking at a weak acid, most of the HA remains as that weak acid. This doesn't mean that it's not dangerous, but most of it stays H plus, HA. Some of it breaks into the H3O plus solution. Any questions? Okay. So we have a term called the acid dissociation constant known as Ka. So if you notice, we're still dealing with our Ks, right? It's just instead of Kc concentration, I'm dealing with Ka because I'm referring to just the acids. So remember, water is a constant. This is liquid. I don't care about it, okay? So my equation is going to be your product over your reactants. Your product is just these two things on top over your reactants. This is the dissociation of your acid. So with that said, the Ka tells us how strong the acid is. Again, not looking at danger, just the strength of the acid. Higher the Ka, stronger our acid, more of it dissociates. I have more H3O plus in my solution. The weaker the acid, the lower percentage of dissociation. In other words, I have smaller Ka values. They're less. Anyone have any questions up to this point? Okay. So some examples here. Again, you don't have to memorize these examples. The next slide we're going to talk about is what you do have to memorize. Okay. So there is a list of strong acids. There's about 6, maybe 7 or 8 of them max that you need to know. If you know how to identify them, everything else is considered a weak acid. So if we're looking at just acids, these 6 to 8 are your strong acids and everything else is weak. So the first ones, hydrohalic acids. So anything in group 17, okay? Plus hydrogen. So hydrogen plus group 17 equals a strong acid. I like to write SA to represent strong acid. The only exception is HF. So fluorine joined with hydrogen, it's partially due to the electronegativity from fluorine here. It's also partially due to the size of the atom itself. It's so tiny that it actually doesn't really hold on to, it holds on to the H more closely than the other ones. Everything else, HCl, HBr, HI, they're further apart, so it's easier to take the H away. So it's easier to separate them and dissociate it. So these are considered strong acids because it's easier to separate them. HF has such a strong hold, the F has such a strong hold onto the H, it makes it a weak acid. Any questions? Okay. With that said, that's the first type that you have. These are the 3 listed here. We'll put them to the side, okay? The other combination is called oxoacids. So the number of protons that you have, referring to the number of hydrogens, versus the number of oxygens that you have, okay? If there are, for whatever reason, 2 or more of the number of oxygens compared to the number of protons, not a ratio, it's 2 or more compared to the number here, then it is considered a strong acid. So if I give you an example, HClO4, there are a total of 4 oxygens and only 1 proton, 1 hydrogen. There's obviously 2 or more, so this is considered a strong acid, okay? H2SO4, same exact situation. There's 2 or more versus the 4 here, so this is also considered a strong acid. If you had something like H2SO3, this is not a strong acid because this does not have 2 or more oxygens compared to the number of protons. Anyone have any questions up to this part? Okay. So these are 3 of the categories you should know. There's also HClO3. This one is also considered a strong acid based on our definition. Okay, so you have these 3 right here, these 3 plus this one right here. And any other combination where you can see the oxo acid shows that the number of protons, or the number of oxygens is 2 or more than the number of protons.
So wait, Professor, those 3 that you have listed as examples are the 6 that we need to know, or is it these
Yes.
types like the oxo acids?
Well, these are the ones that are most common. Okay, so you should know these. In addition to that, they may ask you other ones because the oxo acid definition is pretty standard, right? You have some number of protons, there's some number of hydrogens, right? And then some number of oxygens. If for whatever reason you have 2 or more in favor of oxygens, then it is considered a strong acid. That make sense?
Yeah,
Okay.
thank you.
All right. Now, weak acids is everything else. So if it's not part of my strong acid category, it is considered a weak acid. Simple as that. HF is one of them. You have HCN. Again, these are all things that you don't have to list out. They don't meet the oxo acid requirement of 2 or more protons. Carboxylic acids, when you see COOH, so you're going to see COOH a lot when you get to organic. This is your carboxylic acid. Some of you have probably seen this before. So this is considered a weak acid. Now, this is not to say that weak acids don't hurt. I keep emphasizing this. If you spilled HF on your hand and you don't deal with it right away, this can cause bone damage. Okay, it'll seep down into your bones and cause damage that way. You may not see the damage on the surface, but it'll start damaging your bones from the inside. Okay. Now, in terms of base strength, these are pretty straightforward as well. We have a list. Any metal from group 1 plus oxygen or plus OH, adding to joined with either of these, right, is considered a strong base. I like to use SB for strong base. And then these 3 in particular, from group 2, plus O or OH makes a strong base. Everything else is considered a weak base. Once again, all of group 1 metals, and then these 3 from group 2 metals form these strong bases. Everything else is considered a weak base.
So wait, Professor, you said just those, wait, all stuff.
So
Uh,
LiOH, for example, okay?
yeah,
NaOH, so, or Na2O. These are all considered strong. Does that make sense?
yeah,
Calcium hydroxide, same thing, considered strong. Okay? But if I went
Also-
ahead and I said aluminum hydroxide, right? This is
Yeah.
not a strong base because it's not one of our categories here.
oh, okay. So it's, but now a quick question regarding the little examples there. So it says N2O, so that means it has to be double bond, the oxygen has to be bonded twice. Yeah. Bonded twice to the metal.
Not bonded. Oh, yes, if you really want to put it that way, this is only for group 1. Remember, so you learned about this previously. This is a +1 charge. O
Yeah.
is a -2 charge. So you need 2 of these joined with 1 of these.
Yeah, and then just the group 2 means that it can only bond with 1 oxygen atom, basically.
1 oxygen or essentially 2 of these OHs.
Okay.
Okay.
Oh yeah, that makes sense. Yeah, thank you so much, Professor.
All right. So weak bases, some of the most common weak bases that you will see is ammonia. So whenever you see ammonia, then you know that this is not a strong base. It is a weak base. For those of you in the lab, you will actually work with concentrated ammonia, depending on when you go ahead and do the complex ion experiment or when you go ahead and do the qualitative analysis experiment. Okay. Concentrated ammonia, I believe they said it was something like 15 molar, is very, very volatile. If you had 1 drop of this out of the fume hood, the room smells it, okay, and is not good for you. So I don't know how strict your lab professor is, but I want you to be careful when you are working with this. I don't know if you guys are doing in person or if you're doing part virtual labs, but if you are working with this, leave that in the hood, don't take it out, okay? The second you take 1 drop out, you spill it, that room smells like concentrated ammonia. You don't want to smell that. Okay, any questions? All right, let's continue then. So I want you to go ahead and take a minute, look at these 4 questions and tell me whether or not these are considered strong acid, strong base, weak base, or weak acid, okay? So you can go ahead and just make a mental note. If you have to write down SA, WA, WB or SB, write that down. I'll give you some time to work on this. Okay. Does anyone else still need more time with this? Let's take a look. A here is, I see some people wrote in chat. It is a strong base. Okay. B here is a weak acid because we can see the COOH. H2SeO4. So
Isn't that
it's-
yeah? Isn't that a strong acid?
it is a
'Cause
strong
it's-
acid. So you see the oxo acids, it fits. Okay. And the last one, NH2, that's from our ammonia or amine attached to it. So this is our weak base. Okay. Any questions on these? Okay.
Wait. Oh, Professor, I actually do have a quick question just with the
Sure.
last one. So it's because the ammonia that it's because the N.
It could be the
Yes.
ammonia or it could be the amine. And this one is probably the amine attached to NH2.
Oh yeah. Oh, okay.
Both
Thank you.
scenarios, as long as there is a lone pair that's sitting around here, then that would generate this as being a weak base. Okay.
And it always has to be N, right? It always has to be N in the compound for it to
No.
be.
You can have weak bases that are not N. Remember I looked at aluminum hydroxide?
Oh yeah. Oh,
If
okay.
it's not part of my list that I had before, group 1A, and then some of my group 2s, then it is considered a weak base.
Okay.
Okay.
Thank you.
No problem. Okay, so we're gonna go through this quickly. Again, this one was strong base, weak acid. This one's a strong acid, and this is a weak base. Okay. So the next thing we're gonna talk about, if I take a look at water. Here I have two waters, okay? Is water considered an acid or a base?
Isn't it considered an either? It's considered neutral.
So it is considered neutral sometimes, but it is actually considered both an acid and a base. Okay. So again, it functions as both scenarios. It is an acid and is also a base. So the term is amphoteric. Sometimes they refer to it as amphiprotic. So you can write down either of these terms. It functions as both an acid and a base. Okay, does anyone else have any time with this? All right, let's continue. So other examples would be certain metals plus oxides. examples of copper, zinc, tin, lead, and aluminum. You don't really need to know these. The main one you really need to focus on is just water. Okay. With that said, it is, in terms of its base strength and acid strength, it is very, very, very weak. There's only a little bit of acid and a little bit of base coming out of this water. Okay. So it forms very, very small amounts of H2O plus and very, very small amounts of OH minus. So this is also known as the auto-ionization or self-ionization of water. So water will go ahead and ionize itself. There's a term here called KW. So here you can also see the amount of H3O plus and the amount of OH minus when we split them up. Again, this is liquid, so I do not include this in my equilibrium expression. Okay, so this is gone here. All I have is just H3O plus and OH minus. Remember, this is my acid, this is my base, right? The two of these multiplied together is equal to my KW value, 1.0 times 10 to the negative 14. This is a constant. This is a constant at a particular temperature. So it is a constant at 25 degrees Celsius. If I change the temperature, I change the value of this constant. So if I'm looking at pure water, if the concentration of H3O plus, the acid, is equal to the concentration of the base, I can go ahead and do the square root and find either one of these. And the square root of 10 to the negative 4 gives me 10 to the negative 7. Does this number look familiar to you?
Isn't that
You're right. It is the pH level. Okay. Remember, pH of 7 is equal to neutral. We will learn more about this in a little bit. For now, we're going to focus on just the concentrations of H3O plus and OH minus. So before we even talk about the term pH. Okay. So once again, there's always H3O plus and OH minus in our solution. It's just how much of each I have. Okay. So these are, think of this like a seesaw, okay? They must always equal, the two of these multiplied must always equal 10 to the negative 14. So if I have more H3O plus, I should have less OH minus. So think of it this way. If this was 10 to the negative 7 and this was 10 to the negative 7, the two of these multiplied should always equal 10 to the negative 14, okay? If I increase in the amount of H3O plus, so let's say this was 10 to the negative 5. Remember, 10 to the negative 5 is higher than 10 to the negative 7. The negative here, remember, is referring to how many decimal places we're shifting over, okay? As a response, this should be 10 to the negative 9. So this is smaller than this. They should still equal 10 to the negative 14. Is anyone confused about this right now? No? Okay. So in an acidic solution, you should have a higher concentration of H3O plus. In a basic solution, you should have a higher concentration of OH. If they are neutral, the two concentrations should be equal to each other, the amount of acid to the amount of base. Any questions up to this step? Okay. So to change between these two concentrations, if this number was 10 to the negative, well, let me change the color real quick. If this number was 10 to the negative 5, like I said before, the two of these multiplied should equal 10 to the negative 14. So if I do 10 to the negative 14 divided by 10 to the negative 5, I should get 10 to the negative 9. Right? Because the two of these multiplied should equal 10 to the negative 14. So that's one way of going to trying to figure out, if you have one concentration, you know, you can figure out what the other concentration is because you know the middle one, KW, is 10 to the negative 14. We are assuming this is at 25 degrees Celsius. If I change this temperature, this is no longer this value. These numbers are now equal to something else, whatever that something else is. Most of these experiments will always indicate you are at 25 degrees Celsius or at 20 degrees Celsius, whatever the thing is, to indicate that we have 1.0 times 10 to the negative 14 for a constant. Okay, any questions before we move forward?
so basically it's just the more H3O there is present, the more acidic, and if they're, it doesn't have to be exactly equal, or can it be roughly equal?
Are you referring to the middle piece right here?
Yeah.
Well, then that would change what our value is here. It would be slightly more acidic or slightly more basic.
Oh, so it always has to be equal. Okay.
Yeah. So if it's exactly equal, it is exactly neutral.
Okay, thank you.
Now, if you go ahead and look at the water that we drink on a normal basis, it is actually not exactly neutral. It's more acidic. So different things will make it more acidic. It could be the salts, it could be the other things that are added in, could be the toxins that are there, could be the pollution. So our water is actually more acidic than neutral. You actually don't really have water that's exactly neutral unless you distill the water and there's no ions in it. Okay, any questions before we continue? All right. Now, with that said, I want you to go ahead and use this information right here, calculate the OH, and then tell me if this is an acidic, neutral, or basic solution. You should use KW to help you with that. I give you about 1 minute to figure it out. Okay, so by now you should have figured out that looking at the concentration here, since this is our H3O plus, and that this times my OH minus must equal KW, and this is 10 to the negative 14. So if this is already 10 to the negative 4, to equal 10 to the negative 14, this must be somewhere around 10 to the negative 10, give or take. Okay, I'm estimating it. Sometimes they could be even 10 to the negative 9, depending on what it is. So knowing that fact, right, this is obviously much more bigger than this one. So even if we didn't solve for OH yet, you should be able to figure out that this is acidic. Any questions? Okay. So now we can go ahead and say 10 to the negative 14 divided by 3.0 times 10 to the negative 4 will give us the value of our OH. We know this is something around 10 to the negative 9, 10 to the negative 11, something in that range. Okay. So let's see what they did. We plugged it in. You got 10 to the negative 11. Anyone have any questions? Okay. So now we're going to talk about the pH scale. So generally speaking, scientists don't want to work with complicated large numbers. So something like 3.3 times 10 to the negative 11 gets a little complicated, gets a little annoying to work with. Okay. So we want to work with something called pH, which is essentially known as the power of H, or the power of OH if we're looking at OH. So this is the power of H. So they like to work with whole numbers, makes it easier. If you have a pH of 7, it is neutral. pH of less than 7, then it is acidic. If it is greater than 7, then it is basic. Okay? So we make it very simple in that scenario here. So again, higher the pH, lower the H3O plus, the less acidic it is. Opposite scenario, lower the pH, higher the concentration of this, more acidic it is. The best way to solve for this is just simply the negative log of my H plus concentration is equal to my pH. Any questions so far? So you'll notice a trend here. Let's say I went ahead and I said that I'm looking at just the concentration of H3O plus. This is negative 7. What is my pH for this? Once again, if the concentration is 10 to the negative 7, what is the value of my pH? Plug it into the equation if you don't know what I'm referring to. So negative log of 10 to the negative 7. What do you get? You get 7, right? What if I had 10 to the negative 5? What is my pH? Should be 5, right? 10 to the negative 9, pH would be 9. So it's pretty easy if we're looking at just whole numbers. So if this is 1 times 10 to the negative 9, I don't need to write this part down. 10 to the negative 9, I'm simply taking this number. I'm getting rid of the negative with the negative here. Okay, then it just becomes 9. So that's only if we're looking at it very straightforward. If I have something like 1.3 times 10 to the negative 5, you would have to actually go ahead and put that into your calculator, solve for it here, and get the actual pH value. So it's no longer just 5. Okay? All right, let's continue. So with the scale here, you can see some of the most common things that we have. A lot of our food is actually considered acidic. Okay? Even milk is considered acidic, even though it's very slight, it's only slightly acidic. Everything else up here, anything that is basic, tends to be some kind of cleaning product or your blood. Any questions? Okay. With that said, there have been people saying, oh, you should drink alkaline water. Again, that's like a higher pH. I don't know if that's necessarily beneficial for your body because your body breaks things down with acids. So some of you have probably taken living environment. You know that you have pepsin in your stomach acid with a pH of like 1 or 2. So that helps you break stuff down. So drinking something that is alkaline, in other words, basic, is not necessarily helping you with any kind of digestion or anything along the way there. It may just be a way for them to make some money by selling you alkaline water. Okay. So we can also relate a thing called pKa. pKa is the negative log of our Ka. So it's the power of my Ka. So if I look here, the higher my pKa value is, the smaller my Ka value is. Okay, so it works the same exact way. A low pKa means a high Ka. And then a high pKa means a low Ka. Any questions before we continue? Okay. So let's go ahead and relate pH, pOH, pKw, and where we got this information from. Okay. So we have our original equation right here. Kw is equal to H3O plus times OH minus is equal to 10 to the negative 14. So this is our original value. This is assuming at 25 degrees Celsius. We said that we can go ahead and take the negative log of H plus, that'll give me pH, right? If I go ahead and take the negative log of OH, this gives me pOH. If I take the negative log of this K value, it gives me pKw, okay? So we're assuming that, remember, these two multiplied must always equal this number right here. So I can go ahead and plug in my negative logs for everything here. I get pKw, which is equal to your pH plus pOH. These are related to each other. They must always equal 14. So if pH is 7, pOH must be 7. If pH is 5, pOH must be 9. The two of these added together must always equal 14. So it follows the same format here. The two of these multiplied must always equal 10 to the negative 14. Any questions? So with that said, if at any point you have pH, OH minus, H3O plus, or pOH, if you have any one of these, assuming it is at 25 degrees Celsius, you can find the other three. Any questions so far? Okay. So if we look at this diagram right here, remember the two of these values added together should always equal 14. The two of these values multiplied together should always equal 10 to the negative 14. In every scenario that we go across, it comes out the same way. So this negative 11 times negative 3 gives me negative 14. This 11 plus this 3 gives me 14. That's the relation between pH, pOH, and H3O plus and OH minus. Anyone have any questions up to this part? Okay. So if you want to look for this, this is figure 18.5 in your textbook. We will go ahead. I'm going to go ahead and show you a method of how to calculate each scenario. So there's a little bit of space. This should just be pH. The typo didn't come out. So again, pOH and pH. Okay. So on the outside is we're going clockwise. The inside, the red, we're going counterclockwise. So if I have pH, you haven't learned this one yet, but 10 to the negative pH is essentially just your value of H plus. So if I said pH was 7, this is 10 to the negative 7, which is a concentration here. Okay. So when I get to H plus, I can go ahead and find the concentration of OH minus by simply doing Kw divided that. It gives me the value here. So I'm gonna go ahead and pick a number here. For pH, I'm gonna go ahead and pick 9. I want you to go ahead and solve for POH, OH minus, and H plus, based on the fact that I told you pH is 9. I'll give you some time to work on it. I'm also going to be adjusting the slides real quick, so give me a second. Okay, can you hear me now?
Yeah.
Okay. So really quickly, pH is equal to 9. Tell me what other information you've gathered from this. What can you tell me about POH, H plus, and OH minus? This part requires some interaction from you guys. Okay, POH is 5. The two of these added together should still equal 14, so it matches right here. If you wanted to go backwards, you can go ahead and do 14 minus their pH value gives you POH. Okay, knowing these two now, to get to your OH minus and H plus, you can simply just write this thing down. 10 minus POH, which happens to be 5. And this one happens to be 10 minus pH, which happens to be 9. If you want to confirm it, you can go ahead and move across this way. Again, KW is equal to 10 to the negative 14. Any questions about this? Now, obviously, what I gave you was a whole number. Sometimes you'll see things such as 1.33 for your pH. You have to go ahead and solve for everything else. It's not going to give you a nice whole number in that scenario. Okay, any questions up to this part? All right, let's continue. So why don't we do this? Looking at this equation right here, you're going to go ahead and find all 4 of these for each of these scenarios. So same thing that we just did, except that instead of giving you a nice easy number, you get these numbers to work with. Okay, I'll give you about 2-3 minutes to finish this, and then we'll go over it. Okay, does anyone else still need more time with this? Okay. So let's take a look at the first one. This is a strong acid, okay? So we assume if I have 0.3 molar concentration, I should have that many molar concentration of my H plus present. So my concentration is essentially the same thing, 0.3 molar concentration, okay? I care about that one H, there's only one H present. So with that said, I have my H plus. I can go ahead and calculate my OH minus, my pH, and my POH. So let's go ahead and take a look. Really quickly, concentration is here. If I wanted to find just pH, it's negative log of this number. I get 0.52. This is my pH. If I want a simple way of just solving for POH, you can go ahead and go through this method as well. So they went ahead and did this, then they went ahead and did that. Or you can go ahead and change pH into POH. So it's just 14 minus this number gives you that number right here. Okay, that gets that out of the way. Again, KW divided by 0.3 will give you your value of your OH minus. Any questions on any of this? Anyone lost on it? Anyone not know how to get here?
Wait, Professor. It's always gonna be the log of whichever one you're trying to find, like remaining for like pH. I see up top.
Yeah, so
So
we
is-
have the H plus, right?
Yeah,
We
and
went
that's
ahead
just
and
the
did
log
pH
of
to get pH.
yeah.
Yeah.
Okay,
You
I
get
see.
that, right?
Yeah, I get it.
Okay.
All right,
All
thank
right.
you.
So if you're ever confused, refer back to that graph that I drew with the 4 things. This way it's a little bit easier so you can follow along and do what you got to do. Okay, so the next one gets a little more complicated. If you look here, there are 2 OHs, okay? For every 1 mole of this, I have 2 OHs. So if I have 0.0042, I should have that twice the amount of OH. So that is what I'm starting with, twice the amount here. If you didn't start with this, you're not going to have the right numbers. So you must account for the fact that this is OH2. There are 2 of these hydroxides. Okay, you're going to see this pretty often. So don't let this trip you up. Go ahead and find the POH, you get this value. You can go ahead and get the pH by simply doing 14 minus that number, gives you this one right here. You can go ahead and find the H plus concentration by doing KW divided by that concentration that you have, and it gives you this number right here. Any questions? And just as I said, if you have any one of these 4, you can solve for the other 3. All right, let's continue then. So let's talk a little bit about the decimal places and the sig figs that you see. Now, this is not a standard rule, but generally speaking, if you look here, there's at least 2 sig figs in my concentration, okay? It also means there's at least 2 decimal places in my pH. So in most cases, it follows this trend. If there's 2 sig figs, there's 2 decimal places. 3 sig figs, there's 3 decimal places. You want to make sure you include at least that many if you're dealing with that. Because this number, if it's 2 sig figs, you can have like 1.3 instead. So then that affects the values here for pH. It's not always gonna come out to 7 exact. It has some numbers in the back as a response. Okay. Once again, try to keep these consistent. If there's 2 sig figs, you want at least 2 decimal places. Any questions before we continue? Okay. So the next thing we're going to learn about is the Bronsted-Lowry definition. As I mentioned briefly earlier, Bronsted-Lowry didn't say that Arrhenius' definition was wrong. He didn't say Arrhenius' definition was bad. He simply said, let's expand on it because I feel like you didn't include enough stuff. So Bronsted-Lowry felt like Arrhenius left some stuff out. So he said, I want to focus on the proton. So the H plus ion is the same as Arrhenius' definition of an acid. It makes an H plus ion, okay? Or it makes H3O plus, which is the same thing. But the difference, he said, is that instead of focusing on OH minus, because not everything has OH minus in it, okay? It says, I want to look at things that accept protons. Anything that accepts a proton is considered a base. So previously we learned about ammonia, right? If you look at ammonia itself, there is no OH. So how is this considered a base? In this scenario, because it is a proton acceptor, it will accept a pair of protons, or it will accept a proton, then it is considered a base. And in order to accept it, it needs to have a pair of electrons, a lone pair of electrons. Electrons are negative. So in order to receive the positive charge, it needs to have something that is negative. And then once again, Bronsted-Lowry focuses on definition of proton transfer process. Any questions? Okay. So 2 examples here. HCl is my hydrochloric acid. Okay. This is the one donating the H plus. So the H plus is leaving. It's going towards the water. So my water here is acting as a base. It is receiving that H plus. So remember, water can be a base and an acid. In this case scenario, it is acting as a base. It is receiving that H plus. It becomes H3O plus, and then you have Cl minus left over. Okay. In the opposite scenario, I have ammonia here. This is functioning as an H plus acceptor. So here, my water, being amphoteric or amphiprotic, is going to go ahead and donate the H plus to NH3. So this becomes NH4 plus, this becomes OH minus left over. Any questions? All right. So with the definition of moving a proton only, we have actually come to a term called conjugate acid base pairs. So a conjugate acid base pair referring to this and this right here, these two are related by a difference of one thing, a difference of one proton. So this has one more proton, this is one less proton. And then the two of these, again, conjugate acid base pairs, this has one more proton, this is one less proton in comparison to this. That is what conjugate acid base pairs mean. So if I look at something I wrote before, HCl, if I dissociate this into H plus and Cl minus, this is considered the conjugate base to this acid. Does that make sense? There, it's a difference of one hydrogen. Okay. So in the reverse reaction, if I flip the scenario, right? Here we have the NH4. So this is going in this direction. This one is going in the forward direction, it's going in the reverse. This is functioning as my acid, and this is functioning as my base. In this scenario here, this was my acid, this is my base. Okay. The term conjugate is the difference, once again, the difference of one H. So the acid is here. This is the conjugate base to this acid. That means what this is what's left over after I have lost a proton. This is the conjugate acid to this base. This is what is formed after I have received a proton. So perspective-wise, this is moving in the forward direction. Okay. So this is my acid, this is my base, this is the conjugate base, this is the conjugate acid. In the opposite scenario, if this is my acid, this is my base, this is donating that H plus. So this is the conjugate base of this acid. And this is the conjugate acid of this base. Any questions? Okay. So just as I mentioned before, the term conjugate acid base pair refers to those two pairs together. The conjugate base is whatever is left over after we have lost the first proton. Conjugate acid is whatever the base is after it has received that extra proton. So you can tell about down here, they refer to acid 1, base 1. These two are related to each other. Okay. And then base 2, acid 2, they're related to each other. So it depends on the perspective. If I'm looking this way, these are my acids and bases, these are the conjugates. If I look this way, this is my acid and base, this is my conjugate. Any questions? Okay. So this is just a list of different conjugate acid base pairs. Anything that has a proton that can be given away, whatever's left over is going to be your conjugate base to that. Okay, it's going to have a conjugate acid base pair relationship. All right, let's continue. So I want you to go ahead and look at this. Identify the conjugate acid base pairs in A and then in B. So which two things are paired together? Give you about 30 seconds to a minute to do this. Okay. So let's take a look at the first one for A, H2PO4. Which one is this conjugate acid base paired with?
Isn't it paired with HCO3?
Not quite. It's paired with HPO4 2 minus.
Oh,
The
because
difference
it's
between these two is just one hydrogen. And then these are paired together. Difference is between
Oh.
one hydrogen, okay? The next
Okay.
one, how about H2O? OH minus, and then SO3 2 minus is paired with HSO3 minus. Okay?
Oh, so Professor, basically all it means is that one of them is either gaining the hydrogen, the other one's losing it. That's basically all it is.
Yes.
Okay. Thank you.
So if I said I had some acid here, okay? I'm gonna write it as HA. This is my acid. If I take away this, it becomes A minus. The relationship between these two is that this is my acid here, the HA, right? This on the right side is my conjugate base to that acid.
Oh, okay. Thank you.
Okay. So let's get past all this. We already figured out which ones are pairs. So let's talk about the net direction of a reaction. So you saw that this says going to the right or going to the left, right? We always want to make sure that we are forming the weaker acid and the weaker base. Remember what our definition of weak acid and weak base is. The weak acid and the weak base tend not to dissociate. They tend not to separate as much. So NH4 here tends not to go ahead and get rid of that H plus because it's a weaker acid, okay? But this is a stronger acid, so this tends to break it apart. So you're going to get that H plus leaving very easily. That's what a strong acid and a strong base means. They like to separate easily. NH3 likes to receive an H plus, so it wants to receive one, okay? So once it has received one, it's content. It likes to stay where it is. Any questions? Okay. In this scenario, it favors the product because it favors the side that produces more of the weak stuff. Okay, we're going to talk about a term called, well, we're going to refer back to the conjugate acid base strength. I like to refer mainly to the conjugate base strength, okay? And then to the acid strength. So really quickly, if I look at something like HCl, is this a strong acid, strong base, or weak base?
Strong acid.
Strong acid. What does strong acid tend to do?
Dissociate.
Dissociate. So I like to separate these, okay? They like to remain separated. With that said, if this remains separated, does it want to join back together with an H? If we were to assign feelings to these, if
Yeah.
HCl separates very easily, you have H plus and Cl minus. The Cl minus want to join back with the H.
Yes.
Not really. If it's so easy to separate it, it wants to remain separated. Okay? Think of it like a bad relationship. You broke up from that relationship. That relationship is toxic. You don't want to get back with that person. Make sense?
Yeah.
Okay. Now, another scenario, if I give you HF. HF tends to be a weak acid, right? So it doesn't really want to separate. There will be some separation. You're going to get some F minus and some H plus. Does F minus want to remain separate or does it want to reform HF? This is a weak acid.
Reform HF.
Reform. It tends to want to stay as HF. Okay? So in this scenario, this is going to want to reform HF. Does that make sense so far? I'll take your silence as a yes. So if I have HCl here, and I break it into H plus and Cl minus, this is the conjugate base of this acid. This is a strong acid. This is the conjugate base of a strong acid. Okay? And then I have my HF here. This is a weak acid. I have F minus. This is the conjugate base of a weak acid. If I were to compare these two in terms of strength, which one of these is a stronger base?
Cl minus.
Not Cl minus. Let's take a look at the right side here. If you look at this diagram, right? The stronger the acid, the more easy it breaks things apart. If it breaks it apart and it separates, does that thing want to rejoin and reform the strong acid?
No.
No, right? So then it has no desire to do that. In order to reform, it needs to receive an H, right? So if it has no desire to do that, that means it's actually a very, very weak.
Oh, okay. 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 Got it.
And then the opposite is true. If I have a very, very weak acid, it tends to want to stay as a weak acid. If I have the conjugate base of that, it wants to reform with that H plus. In other words, it wants to really receive that H plus to go ahead and reform my weak acid. Okay. So the relationship here, the stronger the acid strength, right? The weaker the conjugate base strength. Okay. So if I look at HF, this is a weak acid. If I look at HCl, this is a strong acid. So the conjugates of the respective thing, this should be a weak base, and this should be a stronger base, not a strong base. So to clarify this does not mean that this is a strong base. Right? It just means that it is stronger in comparison to Cl minus. Does that make sense?
Yes.
Okay. To give you the relative strength, we like to use water in the middle. So if I have water in the middle, water is a stronger base. We're looking at base strength right now. It's a stronger base than Cl minus, because this comes from the conjugate base of a strong acid. So this is weaker than water. And then F minus comes from a weak acid. So the conjugate base of a weak acid is stronger than water. So we always use water as a comparison. Again, this is from the weak acid, and this is from the strong acid. Okay, we're looking at the base strength, so the conjugate base strength of each one. So F minus is stronger than water. Water is stronger than Cl minus. Any questions up to this part? So I want you to memorize this concept here, okay? And look at this diagram. I want you to memorize this, because things we're going to talk about at the end when we talk about salt yields and when we talk about buffers in the next chapter, if you don't understand this, you are going to be lost. So make sure you understand this concept. The stronger the acid, the weaker its conjugate base. Okay. So go ahead and make a prediction which way this reaction will shift, right or left, because we're trying to determine which one is a stronger one, which one is a weaker one. I'll give you about 1 minute to figure that out. Okay, so let's take a look at this. If I were to compare these with each other, which one is a stronger acid? I can see that this one is going to be my base. This is going to be my acid. This is my base, and this is my acid. Water can function as either one. So looking at this, which one is a stronger base and which one is a stronger acid? The left side or the right side? The right side is actually going to be stronger. The OH itself is just the base. Okay, this is very, very strong. H2S is fairly strong. Not strong in the sense that it's a strong acid, but it's stronger than what this is, and stronger than what water is. Okay, this is an acid that is stronger than this acid. This base is definitely stronger than this base. Okay, so the reaction will tend to shift to the left, because the strong acid and strong base tend to dissociate, and then they will mix and form whatever is left over here. So the weaker it is, the more stable it is. That's a good way of putting it. The stronger it is, the less stable it is, the more it's going to react to the other side. So let's take a look. Stronger base, stronger acid, it's going to shift to the left. So Kc is going to be less than 1. Most of it's going to remain as the weak acid, weak base here. Okay, So one other term I want to bring up here is the relation between Ka and Kb. So we know Ka is our acid dissociation. The higher the value of Ka, the stronger our acid. For Kb, it's the same thing, but this time it's dealing with bases. If I combine the two of these together, and this only applies for conjugate acid-base pairs, okay? The two of these together can equal Kw. And again, this only applies for conjugate acid-base pairs. So if I said I'm looking at HF, and this has a Ka here, right? And I look at the F minus, this is the conjugate base, this has a Kb. The two of these multiplied with each other will equal Kw because these are conjugate acid-base pairs. If I said I have HF with a Ka, and then I said that I had Cl minus with a Kb, these multiplied do not equal Kw because they're not conjugate acid-base pairs. Only if they are conjugate acid-base pairs will this equal Kw, the two of these multiplied. Does that make sense so far? Take your silence as a yes. Okay. Before we do this, just to make sure that we are on track on time, I'm going to go ahead and give you the polls. So you'll have about 3 to 4 minutes to answer the poll questions. Also, just to make sure we're on the same page, for all those who are co-hosting, go ahead and stop the recording. And then I'm going to go ahead and remove the co-hosts so you can be able to access the poll.
Can I ask you a question about Alex for a second?
Sure.
Is it graded at the end of the semester if your pi equals 98, then you got 98% of that? Or is it
No.
graded each
I
week?
grade each objective.
Okay.
So every week that something's due, if you finish 98% of that objective, you get 98% of that.
And after the like
Knowledge
every
check?
week gives you a objective goal, a mini quiz, and if you miss one, then you lose it out of your chart. When does it get graded?
So you lose that's graded essentially at the end. Okay. That's telling you how much you need to turn in at the end. Okay. That doesn't affect your individual objective grades. So your individual objective grades, if you scored a 100 on it and then you bomb the knowledge check right after, you still get that 100%. So there should be a way to check exactly that. I believe it gives you 2 scores. One that is where you're currently standing and one which is your objective score. I count your objective score. So what you've already done in terms of your work, you get the credit for it. So it will not take that away.
Oh, okay. Thank you.
Okay. Give you about 2 more minutes before I close the poll. Have about 30 more seconds. Okay, closing the poll now if you haven't finished. Okay, so if we go ahead and take a look at this real quickly, the first one, if you have a Ka that is very high, that should be the acid is very strong. Okay, it doesn't talk about the danger, it talks about how strong it is. If we look at Kw, it is equal to 1.0 times 10 to the negative 14 at 25 degrees Celsius only. So it is a constant, but it's not always that number unless it is that temperature. So it's specific to that temperature at 25 degrees Celsius only. So number 3, when the pH is high, this means that you have more OH than you do H3O plus. The concentration of OH minus should be higher. Question number 4, when you see pH of 3 and pH of 5, every pH difference is a difference of a factor of 10. So difference of 2 is 10 to the second power, so it's 100 times more stronger, okay? Okay, so we're not going to continue with what we have here. I want to save that for next week. Just some last things I do want to bring up here. I looked at your chapter 13 and 12 quizzes already. I noticed some of you are making silly mistakes. So I want you to be aware of them. Please read the question, okay? If we're talking about freezing point, don't answer and tell me about boiling point. If your friend has boiling point, you may not have boiling point, okay? So please read the question. Anyone have any questions for the time being? If not, I'm going to go ahead and transition over into office hours. You can join and ask more questions there.
Hi, Professor.
Thank you so much,
All right.
Professor. Have a good day.
Bye. Have
Enjoy
a
your
good
day.
day.
I'll see you all next week.
See you
Office
next
hours
week.
will be in about 5 minutes. Okay.
Professor.
Enjoy. You have a question?
Yeah, just about Alex. So,
Okay.
So after, even if we finish, so it gave me a knowledge check, right? And if you lose topics from the knowledge check, like by getting them wrong,
It doesn't
right,
take away from your score that you've already done. Okay.
right?
But what it
now-
does do is you need to relearn those topics in order to move to the next topic.
Oh, I see. So
Okay.
now it's telling me I can go back to chapter 13 objective and redo the topics. Do I have
It's
to
not-
do that?
You don't have to do it unless it's associated with something from like 16, 24, or 17 and onwards. So if
I
it's a topic that's very, very important and you don't get to it, right, it probably won't let you move forward from there. Okay.
Yeah, I was just wondering if I had to do it in order to do the next objective.
If you can see the next objective without issues, then you can just keep going with the next objective. If you can't see it, you may have to do some of those other ones.
Got it. Thank you.
Okay. All right. To answer your question in chat, there is nothing set in stone. I normally don't do any extra credit. There may be a possibility of an extra credit at the end of the semester. It's usually very minor for something that you might have missed. Okay. We'll talk more about that as the semester goes along. Again, it is not guaranteed to be present. So I don't always use it. Okay. All right. Once again, if you're going to come to office hours, I'm going to disconnect and then we're going to reconnect afterwards using the same link.